This video is a live demo for PyAsc Skill Stack user pass. The question is simple. Can a user follow the README-style flow, use local skills with normal opencode session, and get a runnable kernel without touching the internal harness? I will show you that pass live in the Ubuntu terminal. We start with local skills. Run opencode with dashscope glm5, ask for an apps float 16 kernel using a short prompt, and then manually check correctness plus total tick. The boundary is important. This is not the internal harness. The harness is useful for maintainers, but the user doesn't need collectors, CI gates, performance writers or protocol matrices to get a runnable kernel. Before the live run, we record the state of the clean clone. We show current commit git status that the target live apps F16 demo directory is absent, and checksums for readme-md, opencode JSON, and the main skill files. This is cleanliness claim for the demo. We are not proving that the whole machine is sterile. The claim is narrow and more useful. Inside this clean clone, the starting state is visible. No install, rebuild, new virtual env or internal harness step is used during the run. And the only expected change is the generated kernel project. After the run, we show git status again and list all the files that appeared under live apps F16 demo. Next, we run preflight derived from PyAsc Skill Stack README. The README says the repository does not assume a fixed CANN location. It uses CANN home and lists both user-level and system-wide install passes. In this recording, the Ubuntu guest first uses system-wide CANN pass that exists on this machine and fallbacks to the user-level install pass if needed. Then we source setenv sh carefully because CANN script may touch unset variables. After that, we add the simulator library path for ascend 150. We also check the open file limit. The README calls out the same simulator problem for Docker. The CANN simulator creates many temporary dump and log files. On this host, we raise the shell soft limit directly before the live run. If the limit is too low, the simulator can fail with too many open files, and the Python side may then report a misleading JSON parse error on an empty file. This shell raises the limit before opencode starts, so both opencode and the simulator inherit the same safer environment. After CANN, we choose a Python interpreter that actually imports ask and ask2. The repository README uses Python 3.10 for the reproducible local build path. This recorded host has the working ask2 install under a different interpreter, so the demo keeps the README intent but discovers the working Python, stores it as PyAsc Python, and uses that same interpreter for verification. We also set opsmas home and opsnn home. These are not needed for opencode generation. They are needed for the canonical reference runs after apps, because some operators come from opsmas, while rmsnorm, batchnorm v3, and apply-adam use opsnn. The model check prints only provider and model, not API keys. In this environment, the expected entry is dashscope glm5. The live command still sets the model explicitly to avoid ambiguity. Now the user flow starts. The command is ordinary: opencode model dashscope glm5. The prompt is not a harness prompt. It has no protocol ID, prompt variant, Oracle label, timeout budget, or archive directory. It is a short user request. Create an apps operator for float 16, prove it on shape 32 on 4096, run exactly one lunch so total tick is comparable, put the result into the live apps F16 demo, use the already validated PyAsc Python, and do not install packages, rebuild CANN, or run repository test harness. The small shapes are intentionally not part of this live performance proof. Under the white tile aligned only policy, there are separate tail and padding tasks. The target performance cell here is 32 on 4096. The middle section is intentionally sped up. The model reads local skills, opens the relevant documents, writes design notes, implementation, self-review, acceptance review, and verification notes. For the demo, every token of generation output is not the point. The point is that the agent works as a skill stack on its own. It does not ask human to manually read skill files, and it does not move the workflow back onto the user. At the end we have a normal kernel project, kernel Py, README and workflow documents. Now the proof is separated from what the agent claimed. Even if the agent already tried verification, we run the generated kernel manually. The command uses the validated PyAsc Python environment variable, the model backend, and simulator version Ascent 950 PR 9599. The correctness criterion is simple: no traceback, pass kernel output verified, and kernel run complete. That means that the kernel is actually runnable with CANN and simulator setup from PyAsc Skill Stack README path. On this machine, full-ups run can take a minute or two, so a jump cut from the start of the command to the successful lines is fine. Next, we show where the baseline comes from. Instead of using magic constant, we run direct ascent-c reference runner from the canonical opsmath aclnn apps reference. This is not the generation harness. It's only the baseline measurement, the canonical reference site for total tick comparison. The reference site uses the same operator, d-type, shape 32 on 4096, the same CANN Model simulator, and the median of 3 total tick runs. In this recording, the reference site gives ref ticks around 4339. The exact historical number is not the point. The point is that the reference site and the generated site are measured symmetrically. The generated site is measured directly from kernel Py. It uses the same shape 32 on 4096, one lunch, and the same CANN Model simulator backend. The log shows successful simulator run and the total tick for the generated kernel, about 4689 ticks for this recording. The gate formula is deliberately simple: ratio equal ref ticks divided by gen ticks. The live target is ratio greater than equal 0.70. Here, 4339 divided by 4689 gives a bound 0.93. So the generated kernel is not only runnable and correct, it also clears the performance gate for the demo cell. If the ratio were below 0.70, we would say that the live generation missed the performance target, even if correctness passed. One more boundary matters. This video shows the user-facing flow, start from the README-style setup, run opencode, get a generated project, and verify the results manually. We do not present collector scripts such as demo vector ops, py, with option regen, ci gates sh from tests, the performance evidence writer, or protocol metrics flags as part of that flow. Those tools are still important. They help us as maintainers with regression testing, evidence collection, ci gates, and the capability dashboard. But they are not what the user needs to understand in order to get a runnable kernel. The framing is simple. The harness proves project quality for us. The live demo shows the product experience for the user. After the user-facing flow, we can briefly show proof metrics as maintainer context. This is not another step in the live user flow. It is a separate verification matrix we use to check that the demo cell is not only runnable, but also performance relevant. In that table, apps float 16 passes with a ratio around 0.93. Add float 16 is below threshold at about 0.68. Reduce sum float 32 passes with a large margin. This keeps both truths visible. User-facing flow is straightforward, and the internal proof is rigorous enough to show passes and misses honestly. Apps already proved full end-to-end user-facing flow, clean clone, open code, generated project, manual correctness check, and total tick ratio. There is no need to repeat full generation flow 5 more times. That would make a video longer, but it would not add a new kind of evidence. After apps, we show how the same proof loop carries over to other operator cells. 10 float 16 uses aclnn 10 from opsmath, RMS norm float 16 uses aclnn RMS norm from opsnn, batch norm v3 float 32 uses aclnn batch norm from opsnn. For the apply atom D family, this proof path uses apply atom float 32 and the canonical aclnn apply atom reference. Dropout do mask float 16 uses aclnn dropout do mask from opsmath. The operator check does not introduce a new generation flow. We pick one row of parameters, cell, shape, d-type, and kernel path. Then we run the reference site through the ascend-C reference runner. That is a canonical baseline step. Aselinen TAN, aselinen RMS norm, aselinen batch norm, aselinen apply Adam, or aselinen dropout do mask using the same CANN Model simulator and the median of three total tick values. The generated site runs separately through PyAsc gen runner.py. This is important to name correctly. It is not generation through opencode. It is one shape, one lunge, performance extraction for already existing kernel. The arithmetic is the same everywhere. Ratio equals ref_ticks divided by gen_ticks. The final table shows that the performance gate is selective. TANH float 16 passes with ratio around 0.73. Dropout do mask float 16 passes with ratio around 0.74 with one caveat. The generated site uses dense mask representation, while the canonical reference uses bit-packed mask. RMS norm float 16 also passes ratio, but it shows a regression when CCE-SIMD via fusion is enabled. The best mode for that cell is fusion off. Batch norm v3 and apply Adam are useful correctness evidence, and vector fusion gives some improvement, but they do not pass the performance gate. That is part of the result, not something to hide. The value of the methodology is that it shows pass, regression and perf miss with the same comparison. The same evidence is also published on the GitHub pages PyAsc Skill Stack dashboard. The same evidence is also published on the GitHub pages PyAsc Skill Stack dashboard. The dashboard is a maintainer view updated by the report-only perf gate. It is not the step user performs in the live flow. The performance panel shows the same ratio, which equals to ref_ticks divided by gen_ticks on ascend 950. At the time of this recording, the nightly gate clears 6 of 9 cells, while add, batch norm v3 and apply Adam are shown as misses. The SIMD fusion panel compares CC-SIMD via fusion compiler flag off versus on the same generated kernels. 2 cells improve, 2 are neutral, and RMS norm regresses. So the story is not that the fusion saves everything. The story is that we measure one compiler flag and separate pass, neutral result, regression and perf miss honestly. Before closing, 3 caveats should be explicit. First, apply Adam D. In this video we call it the apply Adam family. The reference pass uses the canonical ACLNN apply Adam reference. We do not present it as pure apply Adam D against ACLNN apply Adam D. Second, dropout do mask. The generated site uses dense mask, while canonical ACLNN dropout do mask uses bit-packed uint8 mask and unpacks it on chip. The ratio passes, but the comparison is not perfectly apples to apples. Third, vector fusion. RMS norm regresses with fusion on. Apply Adam and batch norm v3 improve, but still miss the performance gate. So the final story is the user proof shows a normal opencode experience, and the post-ups block shows a strict and honest total tick comparison for the remaining cells. Where it passes, we say pass. Where it misses, we say perf miss. The internal harness remain a project verification tool, not part of the user-facing flow.